So you can read the dataset from URL also, but let me not go into that deeper mode. Let me import the same things what we generally do. Let me write the steps. And then last time, if I remember, we were doing some clustering analysis. So let's take the same data set. We are working on some data set, if I'm not wrong, on iris data set, right? Yeah, it's here. So as I told, in Skill-Lync, there is one module by name datasets, and in datasets you will have a lot of datasets, okay? And from those datasets, I'm just importing one of the datasets, which is load underscores iris, which is iris dataset, okay? Now if I print iris, so you would notice that it's very difficult to understand because it has those sepal length, sepal width, and also on, right? So for that, what we have done last time while working on SVM, we have created a data frame out of this, because if you check the directory, you will notice that it's not a Panda data frame. You can also check that. But meanwhile, quickly, let me do this thing. Okay, so now instead of printing the iris dataset, because it's not a data frame now, you can check that. Let me keep it here. So I'll run this code. Now what you'll notice is I ran my PCA Python file here. It says that directory means it will tell what all different things it has in dataset of that iris dataset. It has some description, it has some data, it has feature names, it has file name, target, and target names. But for us, what is important? Data, target, and target names, right? You can also check what is the type of this iris, which is a kind of sklearn bunch. It's not a data frame. So now I'm converting that into data frame. Okay. How I am doing it? Using pandas. Panda.dataframe. I am taking this iris. From iris, I am taking this data. I'm taking this data, and then I'm converting that data into some columns with iris.feature names. So there is one feature names separate tab in your directory iris. So based on that feature names, now this data will have this kind of feature names, which are sepal length, sepal width, petal length, and petal width. So these are the column names which are extracted from feature underscores names, which is already there in iris dataset. And these are the data points which we are extracting from the iris dataset and putting it into the data frame. Now if I print data frame, we will get nicely something like this. See, if I don't do this, no, you will notice that you will not have this proper feature names here as column names. Okay, then will be very difficult to understand which is sepal length, which is sepal width, which is petal length, and which is petal width. And then I am concatenating new column by name target, which is equal to iris.target. Okay, and then that is our output, right? Which is 0, 1 or 2 or 3, I believe, based on number of outputs which we have. Yeah, 0, 1, 2, because we have 3 outputs, target names, right? Which we have already seen in while doing SVM analysis. Setosa, versicolor, and virginica, right? So these are the target names which we are seeing, and the targets are based on 0 as Setosa, 1 as versicolor, and 2 as virginica. Okay. And then I'm using this describe syntax so that I can do this some basic exploratory data analysis to count number of records, to check the mean, identify Q1, Q2, Q3, Q4, Q0. Okay, so these are very basic analysis which I'm doing. Now once I have the data frame, now what I will do here, rather than taking it from the URL, I'm just taking directly from the scikit-learn. Now what I will do, see, there are two ways to standardize this data set. If you remember, if you want to bring the range from 0 to 1, you have to use x minus x mean divided by x max minus x mean, or by using z scores, x minus mu by sigma, right? So I think we have already used that once, x minus x mean divided by x max minus x mean in our one of the sessions. Let's use x minus mu by sigma. So you can calculate mu and sigma for all the features, and then you can do it manually, but there is an inbuilt function in Python which I'll be using now. Okay, so I will be using then inbuilt standard scalar which will use z scores. Okay, and now what I am doing is, here I'm separating x and y, but you don't have to do it, but it's up to you. So separating x and y by using new variable which has all these columns. Okay, and then separating it y also. If you don't want to do that, it's up to you. You can do it in a different way. It's up to you. Okay, so before concatenating here targets, you could have done it here itself. For example, df. So on df, here df has only input features, but that this df would have output feature also. So you can convert this as some new data frame also, df1, and then you can have df1 here, and then it's up to you whether how do you want to play with the data set. Okay, so let's run this till here and see if it is working. I'm not sure if it works or not. Let's not print everything because it's waste of time now, because we have already checked it is printing the right values. So we are getting some error. So let's do one thing. So let's call this x df underscores x, and this is your final data frame which has targets also. So now let's have it only y in this. Say this has iris dot, or let's say new data frame with target. So there is some mismatch with the names. I believe that's the reason I'm doing it with the same names. So let's make sure that all of them are working fine in first place. So let's run this. Let's see if you're getting some error. So df is not defined. Okay. So let's this be df. This is a data frame. We are concatenated. Now let's say df underscores y has only target and df underscores has df of all this, right? Why is it not giving me a drop down? Let's run this first. Okay, this makes sense. Now my data frame y has only target names. Let's print that. Yes, it makes sense. It has only target names. So what we have done, we have got a final data frame with all the inputs and the output. I'm just trying to segregate that into df underscores y, which has output, and df underscores x, which has only inputs. So rather than taking all those columns, let's drop target from original data frame. Okay, and let's drop this. Say target. Now let me use the axis equal to 1. Now let's print this df underscores x. See if we are in the right direction. Let's see that. Okay. Yeah, so it makes sense. So now we have got df underscores y, which has only targets, and df underscores x, which has all the input features, right? Now, can you tell me why I've written, while dropping this target feature, why I've written axis equal to 1? So axis equal to 1 because we are trying to drop a column, right? So when we're trying to drop the column, the axis should be equal to 1, okay? But when we are trying to drop the record, any row, the axis value, try to find what would be the axis value when we are trying to drop the record. But here we are trying to drop one of the columns from the original data frame df. That's the reason I'm using axis equal to 1. So axis equal to 1 means 1 indicates column. Okay. So now I got this df underscores and df underscores y. Let's import StandardScaler because we want to standardize the features, right? So now, as you can notice, our input features are changed from these values to our new values using StandardScaler, right? Now, if you notice, there are some values which are going from negative with a sign also, it is going more than 1 also, because now we are not constraining the values from 0 to 1 using that x minus x mean by x max minus x mean. What we are using here is z scores, x minus mu by sigma. So it can have negative values also, okay? Making sense, right? So we have converted our input features into standardized values. Now let's go to PCA. You could have implemented PCA on the original data set also, because all the units and the scales the scales, if you notice, for all the input features are same, but it's just that I wanted to display this standard scalar as a new function so that you don't have to implement x minus mu by sigma every time in Python. That will be directly done by this function standard scalar, and then transform your input features, and then the values which you will be getting will be based on x minus mu by sigma. Or if you want to create your user defined function by your own, that's also fine. Okay. Now from sklearn, I'm importing PCA, and then what I'm doing is I'm trying to come up with a PCA new variable and implementing this PCA function on getting only two components. I'm just making sure that I get only two components this time. Okay. So this is the way of working in Python. There is another way by which you can work, but this time what I'm doing, I'm compiling the code to come up with only two components. Okay. By using this syntax. Now principal components is equal to PC underscore transform. So what I'm trying to do here is I'm trying to come up with I'm just having two components in the principal components, and those principal components are going with transform on input features only. So input feature should be this time the standardized input features, right? Okay. I'm creating a new data frame out of this principal components. Okay. Now this principal components will have only two components because I'm using two here. So I'm creating a new data frame with this principal components variable which has columns principal component 1 and principal component 2. Okay. So that's how the function has been defined for this PCA. Okay. So that's the reason these are the names. Okay, and you can change the names also, but it will have two columns. Okay, I think you can also change the column names. Let's try that. So now let me run this. So till now what we have done, we have come up with the principal components in the code. Now let me run that. I haven't printed that. Let me print this. So it's necessary that we have to make this data frames into pandas data frames so that we can have consistency. That's the reason I'm making a pandas data frame. And then the column names are principal component 1 and principal component 2. If you want, you can also convert that into, I think, PC1 and PC2. See, PC1 and PC2. Okay. Now the final data frame would consist of this PC1 and PC2 and the targets from the original data set, right? Okay, so let's add that targets here in our final data frame, which is this, and let's print that also. So now the data frame what we have is not with the original inputs, it has principal components and output. Okay, so these are the ways how we can plot this principal components. Okay, so if you want, you can check this, but that's not in the interest of this, but we'll do that later. But for time being, I want you to show something very important. I want to run this now. So this PCA variable which we have used, remember, this PCA has this parameter, and just check that what does it comes out, what will be the output of this. What is this explain variance ratio? What is this denoting these two values? Amount of information. So PC1 has around 72.9, 6% of the data information and 22.8 data information is carried by PC2. So now you must be thinking, where are the remaining information? If you add these two, that would be around 95% of the variation of the data, right? Where is the remaining 5% of the data? You know the answer, which is PC3 and PC4. Okay, let's do this. If you want to visualize, let's visualize the principal components also. So I'm just plotting a figure, empty figure with this size. I'm setting up the labels. This should be PC1, right? Because we have already changed that. PC1, PC2. The graph title should be 2 component PCA. Okay. Font size. Okay. Targets, we know these are the targets. And the colors would be, Setosa would be in R color, red color. Versi color would be in green color. Virginica will be in blue color. Okay. And then I'm plotting a scatter plot. So it would be very difficult to explain you the each syntax here. But let's plot this and then you will get an idea what I'm trying to do here. Principal component 1. Okay, I have to change this also. Okay. Future warning. No problem. It is not showing the points. Okay, let me see what's wrong in this. So now, doing the same thing in a new different data, the reason why I'm doing it to a different data so that you come to know the various ways of solving or doing PCA. So if you remember, here we have done PCA by using number of components, right? But the other way of doing is from Skill-Lync dataset, I'm just fetching another data which is fetch underscores ML data. Okay. Because if you notice, the previous dataset had only 4 features, right? So you will not come to know its importance. If you notice this dataset now, it will have lot many features. Let's do that. I think it is still reading. Okay, never mind. So what I'm trying to tell is, let it read this because it has a huge data and then it has around 700 features. So what I'm trying to do here is, now here it makes sense if you use principal component analysis because it has less amount of RAM, so it takes a lot of time. Anyways, so I'm just reading the data, I'm printing it. I should have not printed it. Okay, it's a huge data set. So from Skill-Lync, you all know this from model selection, train, test, split, and splitting the data. And then I'm giving some 4 variables: training, images, test images. It has images actually, yeah. And then train labels and test label. So this data would look like something. You will have the images in the input features, 8, 1, 2, something like that. And then the corresponding label will be there. 0, 1, 2 or something. Okay. So there will be images and the output feature will be telling its label, whether it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now in your output features, you have 10 classes. Okay. The server has closed the connection. Never mind, I think it's taking a lot of time, so you can try it in your laptop. So I'm just splitting the data set: X, train X, test X, train Y, test Y. Okay. So in the data we have, if you want to notice, let me try once again. So in the data you have images, and in the target you have labels. Okay. So let me try that one more time. It's a huge data set. That could be the reason that. Meanwhile, it runs again. Let me explain this. So we got train X, train Y, and test Y. And then again, I'm from sklearn pre-processing. I'm importing StandardScaler for converting my data points into z-scores, right? So if it prints, then only it will be easy to understand. Let's wait for a couple of minutes. Okay. So these are just warnings, so we don't have to worry. I'm just trying to identify what's wrong with this. Okay, there is some issue with this, so don't worry with this. Okay, let's remove this, but let me complete what I wanted to show in the same data set itself. So if you remember, in this data set, what we have done, we have taken n underscores component equal to 2. By this, we have told that we need only 2 components. The other way of doing it is just write the value, the confident value which you want. Okay, and let's run this again. So now you would notice you would get the same answer. Okay. Now if you try to come up with here, say PC3, let's say that you're coming up with PC3 also. Okay. You are getting value error. Shape of the past value is 150,2, indices imply 150,3. But it's quite simple that we understood that from the previous solution that the already 95% of the information was carried by only 2 components, right? So if you want 3 components, maybe we have to increase the value of this. Say, let's say 0.97. Now it makes sense, right? So if you notice, PC1 has 72.9% amount of information of the variation of the data. It has 22.8% of the data information. It has 3%. So now 73 plus 22, 95 plus 3, 98, and this summation 99.4. So you have around 99.4 amount of information, variation information of the data in this 3 components. Okay, so that is what I wanted to explain here. So but it would be confusing if we write here value and then we don't know how many principal component carries this amount of information value. So generally you can write n underscores component whether equal to 2 or 3. You can start with 2 and then check how much amount of information was it carrying with respect to this function, explain variance ratio, and then you can increase the number of components 2, 3, 4, and then check how much amount of information are coming up. Okay, now for example, here I have written say 0.95. If I write PC3, then it was giving error because we know that 95% of information was carried by PC1 and PC2 only, but I am also looking for PC3. But when I do this PC analysis, it will come up with only 2 principal components based on this 95% confidence, right? So that was the reason it was throwing error when I write PC3 here. So that's the reason I have changed this value to 0.97. Now let's see that if you want all complete information, you would notice that PC4 will have very less amount of information. Let me write, it's not taking. See, PC4 has very less 0.5 amount of information carried by PC4. So that's the reason in general we do not use PC4. If we have 4 features, there is no use of converting it into PC1, PC2, PC3, PC4, right? So that's the reason I always tell use the other option, n underscores component, and based on the components 2, 3. If it is 2, then just write to PC1, PC2, and then check the variance ratio. That would give you the solution. Okay. So there are 2 ways by which you can solve this problem. If you are writing 2, then remove this and then run it. Okay. So there are 2 ways of running PCA. Either you can write n underscores component, or you can write the amount of information, the amount of variation which you need. But then if you write the amount of information which you need, you have to make sure that you are writing right number of principal components. That would be really difficult to determine without doing trial and error. So that's the reason I always use n underscores component. Okay. So tomorrow we'll see why this plot was not working. And then I'll try to reduce the data set here and then see if I can use this data set again to showcase to demonstrate it. Okay. But meanwhile, the objective is clear. This is what I wanted to explain, that there are 2 ways of incorporating principal component analysis in Python.